Hello, hello everyone. My name is B. Abhinandu. I am from CSIT. My roll number is 21951 A3302, and my applied physics AAT concept video is about optical capillary fiber mode interferometer for pressure sensing. Let us look about that. Let's coming to introduction. We propose and demonstrate a pressure sensor based on a micro air bubble at the end facet of a single-mode fiber fusion spliced with a silica tube. When immersed into a liquid such as water, the air bubble essentially acts as a Fabry-Pérot interferometer cavity. Such a cavity can be compressed by environmental pressure, and the sensitivity obtained is greater than 1000 nanometer kilopascal, at least one order of the magnitude higher than that of diaphragm-based fiber tip sensors reported so far. The compressible Fabry-Pérot interferometer cavity developed is expected to have potential applications in highly sensitive pressure or acoustic sensing. Pressure sensing is one of the most important applications of fiber optic devices in industrial and environmental safety monitoring. Various types of fabric optic pressure sensors have been demonstrated to fulfill specific pressure applications, including fiber grating, photonic crystal fiber, and devices and interferometer. And the pressure sensitivity achieved is typically on order of 10 pm MPa. Among above mentioned configurations, the pressure sensors that are based on Fabry-Pérot interferometer have shown promising results for static and dynamic pressure measurements, as well as other physical and chemical parameter detection such as temperature, strain, and refractive index. The Fabry-Pérot interferometers can achieve extremely high sensitivity and flexible demodulated in the wavelength domain and frequency domain, or simply use light intensity detection. For static pressure sensing with high sensitivity, micro micro FP cavity built at the optical fiber end has been investigated intensively. A pressure sensor based on micro FP cavity commonly uses as elastic diaphragm at the fiber tips such as SiO2 silica, polymer, silver, and graphene film. The pressure sensitivity of the diaphragm based fiber tip FP sensor is defined as the ratio of FP cavity length variation to the pressure change, which critically depends on the size and the mechanical quality of the diaphragm employed. While a silver diaphragm with a diameter of 125 μm exhibits a sensitivity of 70.5 nanometer kilopascal, a high elastic graphene diagram with a diameter of 25 micrometer has a sensitivity of 39.4 nanometer kilopascals. Obviously, the small size of the diagram in a miniature sensor did impose a limit on its sensitivity. Second, principle of the compressible FP cavity sensor. By immersing a single mode silver fusion spliced with a section of silica tube into liquid, as shown in the figure, a microbubble is naturally formed by capillary effect at the end of facet of SMF. The air-liquid interface acts as a light reflector which together with the air SMF interface forms a FP interferometer. The length of the FP cavity is highly sensitive due to the environmental pressure, as air can be treated as the ideal gas in a pressure range between 1 and 10 bar. The behavior of the air bubble can be described by well-known ideal gas law as PV equals to nRT, where P, V, and T are the pressure, volume, and thermodynamic temperature respectively of air in the FP cavity respectively. N is the amount of substance of the air, and R is the ideal gas constant, which is and its value is 8.31 joules per Kelvin per mole inverse. The geometry of air bubble in the FP cavity can be considered as a cylindrical instead of spherical, with initial length of L0 at the normal pressure and diameter of D. Thus its volume can be calculated as 2V dl equals to pi by 4. By assuming an isothermic thermal process and substituting values of V in equation 1, and it is equation 1, the pressure sensitivity of compressible FP cavity can be delivered as, like this picture we can see the pressure variations. Experimental results and discussions. In our experiment, in a silica tube with inner and outer diameter of 75 by 127 micrometer was used. The silica tube was a fission spliced with the conventional SMF and then cleaved at a position of tens of micrometers away from the splicing joint. The open air cavity in the silica tube was subsequently immersed into water, which was filled into the tube due to capillary effect, and as a result an enclosed air FP cavity was formed as shown in the figure, where the length of the silica tube and the air cavity are 114 and 90 micrometers respectively. The initial length of the air cavity L0 at normal pressure could be controlled by use of silica tube with accurate cleaved length. Accuracy of less than 5 micrometer can be achieved with the assistance of optical microscope. Figure 2 displays the reflection spectra of air cavities with the initial length of 44.7, 96.8 and 142.2 micrometers respectively, which considered to the silica tube lengths of 57, 116 and 151 micrometers respectively. The fringe visibility obtained is greater than 15 decibels for all the above mentioned cavities. The fringe visibility would be decay quickly with increase in the air cavity length, and for cavity length of larger than 300 micrometers, the fringe visibility of less than 1 decibel was obtained, owing to the curvature of the air-water interface and loosey light guidance of silica tube. The pressure response of compressible FP cavity was studied by compressing the air cavities of different initial lengths. Samples were put into a water cell that connected with nitrogen gas cylinder, and applied pressure could be adjusted with an accuracy of 0.1 bar. Figure shows the reflection spectra of an air cavity at 1.5, 3.0 and 5.0 bar respectively. It can be found from figure 3a that the fringe visibility can be enhanced by increasing the applied pressure, the cavity length and the free spectral range under different pressures are plotted in the figure. An average pressure sensitivity of 3.04 micrometer kilopascal is obtained between 1 and 1.5 bar, which is nearly 2 orders of magnitude higher than that of the most sensitivity diaphragm based fiber tip sensor reported recently. The pressure sensitivity can be further increased by employing an air cavity with longer initial length. The cavity with 0L is 1063 micrometer. The average pressure sensitivity obtained is 6.9 micrometer kilopascal between 1.0 and 1.3 bar. Within a higher pressure range such as 9 to 10 bar, the average sensitivity is 161 nanometer kilopascal, much higher than the achieved in the state of art. As we can see the below discussion in this diagram, where the wavelength peak power is in dBm and wavelength is in nanometer. Pressure and wavelength are nanometer and kilopascals. Okay, right. One visibility sensor. By assuming an initial length of and room temperature of 300 Kelvin, the temperature induced cavity length change at normal pressure can be estimated to be 333 normal nanometer according to the equation 5, and hence the temperature cross sensitivity can be calculated to be, which is slightly lower than that of silver diaphragm FPI sensor. for the static pressure measurement with an accuracy of greater than 10 kilopascal. The pressure measurement error induced by 1 degree Celsius of temperature fluctuation could be neglected. Otherwise, the temperature must be calibrated to ensure the pressure measurement accuracy despite of high pressure sensitivity achieved. There are still problems that need to be further investigated, especially for the stabilization of an air bubble and hence enhancement of the interference fringe visibility at longer cavity lengths. When used vertically, the air the air bubble is stable at the precise pressure. However, for more versatile applications, the cavity geometry should be optimized by considering the fluid dynamics behavior of water. Before a stable air bubble can be maintained, this may be achieved by tapering down the silica tube at the water entrance or blocking the silica tube with optical gel at the water entrance and followed by drilling a microhole by use of femtosecond laser micromachine. The fringe visibility may be enhanced by use of liquid of higher refractive index or chemically treated silica tube that exhibits a flat air liquid interface at longer cavity lengths. Moreover, the hollow core photonic crystal fibers, which exhibit lower transmission loss than that of the silica tube, can also be used to enhance the fringe visibility. Conclusion. In the conclusion, we can demonstrate a compressible fiber optic micro fabric petrocavity for pressure sensing with extremely high sensitivity by immersing the silica tubes sliced at the SMF fiber tip into the water, and air bubble is naturally formed and effectively acts as micro FP cavity. Such an FP cavity can be compressed by environmental pressure and exhibits a sensitivity of greater than 1000 nanometer kilopascal at normal pressure, which makes it ideal for pressure and acoustic sensing in gases and liquids. For compressible FB cavity is expected to have potential applications in statistical pressure measurement, liquid level monitoring, and hydrophane sensing. Thank you all.